Hi. Okay, so in the last two videos I showed you how Gaussian elimination can cause round-off error when you have multipliers that are very large due to having basically very small pivot points. And then in the video right before this I showed you that you could avoid causing errors from avoid these round-off errors by permuting or switching your rows so that your pivot point was always much larger than, or was always the largest value within a row. Alright, at the end we said, okay, well, if we have this decomposition, we also need to keep track of those pivots or those swaps that we make in a permutation matrix. So we had, if I say, alright, I'm going to create this matrix P, which is called my permutation matrix that keeps track of those swaps, and what I want is for P times my original A, 10 to the negative fifth, 3, 2, 1, I want that to be equal to my LU decomposition, or essentially equal to my A matrix time with all of the rows that needed to be swapped. So in this case we had 2, 1, 10 to the negative fifth, 3, right? So we had there's only 2 rows, we'd swapped them. Okay, so the question is, what goes in here so that we're storing that swap, so that this equation holds, P times LU with the rows swapped to avoid those multiplier errors. Okay. So you can pause the video for a second and try this out on your own. How can we make it so that this matrix times this swaps the rows? Alright, hopefully you've come up with this. Basically what we want is, in this first entry, right, we want this row times this column to give us 2. So we don't want to grab this 10 to the negative fifth, so that's 0. We do want to grab this 2, so we're going to put in a 1. Alright? And then for the second one, and that also, if we look, we have, for this row, to give us this entry, we have 0 times 3 plus 1 times 1 gives us 1. Great. Alright, now for the second one, we do want to grab the first entry, right? So this row times this column, we want to get the 10 to the negative fifth, and we don't want to grab the 2, so that's going to be a 0, which again, if we have 1 times 3 plus 0 times 1 gives us that 3. Great. Now, you might notice that this permutation matrix looks a lot like our identity matrix, except that rather than having the ones along the diagonal this way, it has the one along the diagonal that way. And that's actually not a coincidence, and you can use it as a rule of thumb for creating these permutation matrices for larger dimensional systems. So generally, if we start with the identity matrix, so I'm going to write that as 1, 0, 0, 0, 0, 1. Okay, so if I have my identity matrix, all I have to do to get my permutation matrix is switch if we're going to swap rows I and J in our A while we do LU, then we can basically we're going to switch rows I and J in the identity matrix, but we need to do it when I and J are swapped during Gaussian elimination. Okay, so if we were swapping the first two rows, we would swap those. If we swapped, if later on when we zeroed out to here, for example, we were swapping rows, I don't know, 5 and 6, you would swap rows 5 and 6 in the identity matrix. All right. And I'm not going to go through an example of this, but if you want an example with a 3x3 matrix, you can look at example 11.10. What it basically does is it goes through the different steps of Gaussian elimination for that 3x3 matrix and shows you step by step what L is, what P is, and what U is. Not in that order. I think it's actually P, L, and U as you go through the Gaussian elimination steps. Okay. So in the next video, I'll talk about how we can actually use this decomposition of A into P, L, and U, which hopefully you can see how you would say A equals P inverse times LU. But in the next video, I'm going to show you how you can use this decomposition to solve the problem AX equals B.